the solution or the resolution to this Bekenstein-Hawking black hole entropy problem is immensely valuable, but it doesn't directly demonstrate the existence of strings, which is still far from, my understanding is that it's far from generally accepted. What I've heard from a lot of astrophysicists on an unrelated note is with regard to certain extraterrestrial speculations, they say it's not aliens until it's aliens. And I have the sense that a lot of physicists have something similar in mind. They just think it is not strings until it's strings. And you said a few minutes ago that if we had a powerful enough microscope, we could observe strings, but unfortunately we don't have that microscope. So even though this might be purely hypothetical, given constraints of funding or energy, how might strings be directly observed or detected?
Yeah, you're going to get very different answers to this question from people that you interview, and I like think that. I don't think my view is really I have kind of a minority view. And so what happened was, string theory as a theory of quantum gravity and so on, as we discussed at the beginning, was discovered in the early 70s. And then, but it was thought that it, in principle, was incapable of describing the real world. And one way of summarizing what happened in the 80s was it was found in around 85, where there was a kind of big explosion of interest, was that in principle it could actually describe the real world. And not only could it describe the real world, but it wasn't very much of a stretch. You didn't have to stand on your head. The structures that we see in the real world come very naturally out of string theory. So it's always a good thing. You don't want to have one theory which solves every time you have a new problem, you make a new theory. You want a new theory to solve a number of problems. You should be getting out more than you put in. So string theory, you might have thought in the 70s it was constructed, some structure that was dictated to solve this infinity problem in quantum gravity. But now if that same structure also produces quarks and leptons and parity violation and generations and all that kind of thing, then that's exciting. And then, of course, it's also, to link back to what you were saying a minute ago, it's exciting that the same structure also can solve the problem of counting the gigabytes. So one thing, you're getting out more than you put in. Now, in the 80s, when it was realized it could describe the real world, there was a lot of excitement, and we didn't really understand how many ways. One way of saying this is we didn't really have a very good understanding of how many possibilities there were from getting from 10 dimensions to 6 dimensions. That is, I'm simplifying a little bit here, but how many collabio spaces there are. And if there had been, so when I first realized that collabio spaces could be used to get string theory from 10 dimensions to 4 dimensions, I didn't know very much math then. I was actually friends with Yao. I hadn't really worked with him, but we were friends, and I remembered some things he said. And I knew that there was only one collabio space in 4 dimensions, but we needed a 6-dimensional one. And I went to the library and I took out his paper, which I could barely read. I didn't know any algebraic geometry then. And I saw that there was one collabio space that was 6-dimensional. There was one mentioned in the paper. And I thought maybe that was the only one. And if that had been true, there would have been a huge amount of uniqueness in string theory. And there is, in some sense, uniqueness, but before we published our paper, Yao had told me he thought there were tens of thousands of them, and now the number and kind of cousins that can also be used has gotten enormous. And so there is no obvious way to, experimentally verify string theory, short of building an incredibly powerful microscope and seeing them directly. Now, but hold on a second. So people didn't give up on that idea that you could somehow make direct predictions from string theory. I gave up on it. It seemed unlikely. Rational people that I would disagree with, but I don't think they're stupid. I just don't think that they're balancing the facts right, could disagree about whether it will someday be possible to make predictions from string theory. I don't think so. I don't think you could get lucky. You could find some generic imprint from string theory. But I gave up on the idea in 1987. So I haven't thought since, and then I was in a very small minority. But now lots of people would agree with me. So I don't think that string theory is that we're going to measure strings. Yet, you can ask me, why am I working on it? I can answer that question. But I don't think that we're going to... I'm glad that other people are trying to do it. I don't think it's stupid to try to do it. If nobody else were doing it, I might feel obligated to do it. But I think it's a losing. I work on problems I think I can make progress on, and
right.
I don't think making experimental contact, sadly, is going to be possible for string theory. And I think we don't know what string theory, how it will fit in. And my feeling, and also there's I think a false dichotomy out there that string theory is either right or wrong. And I don't think it's a black and white thing. The real question is whether string theory is useful and whether we've learned good things about it, from it. You learned useful things from it. And I want to go back to what the example I gave in the very beginning of the Yang-Mills theory. Yang-Mills theory was wrong. We know now it's wrong. It does not explain the relationship between the neutron and the proton. It explains everything else. Yang and Mills didn't mention that. But, so it explains everything else. They didn't quite see how it fit in. So I think there's plenty of room, and it has already happened to some extent, that string theory will that the space of possibilities about how our subject might develop is really big, and we can't map it out now. And we're trying to find problems we think are important and interesting, like the black hole problem, and try to make everything fit together and explore the space of possibilities. And it's a huge, it's a massive undertaking. I like to talk about black holes. I'm very interested in black holes, obviously. Schwarzschild found the black holes in 1915. It took 100 years to see them. It took 50 years for people to be convinced they exist as mathematical objects. Another 50 years for the world to, really believe that they're up there in the sky. We're still struggling with their quantum nature. So these problems are big problems. They're exciting problems. They're deep problems, but they take a long time, and we don't do very well. If you had asked the founders of quantum mechanics what quantum mechanics was good for, it's too bad nobody did. But how quantum mechanics, how it's changed the world, and the technology, how it fits in together with relativity, it's a wild story that they wouldn't have dreamed of, in the 10s and 20s, the early part of the 20th century. And I think the way that we'll look at string theory in 100 years will be very different. And by that, I mean this whole big body of knowledge that we call string theory. In 100 years will be very different than how we look at it now. But I would bet a lot that it will be important, that it will be a piece of the puzzles that we have put together. That I can prove it, but I'm betting my life's work on it.
Well, I have a couple of things to say. One, you said I might ask why you choose to work on string theory given what you've just said, but I think I can answer that myself, and you can tell me if I'm wrong. But given what you said earlier, you chose to work on string theory because it's a tool, and we can see how that plays out in your career. I mean, it solved or resolved the Bekenstein-Hawking entropy problem that had eluded more classical or quantum approaches to physics for 25 years. And this isn't a new approach by you, this sort of instrumentalism. I mean, Aristotle was an instrumentalist about like geometrical figures for geometers. You didn't have to think that this was a real sort of Platonic thing that you were drawing or aiming at.
Interesting analogy. I've heard that. Yeah. Nice analogy.
To be able to use it. Or Leibniz, for example, in the calculus, he did not believe. It's
very hard for us now to think of triangles as not being real, but yeah, that's a very interesting. It must have seemed that way back then. Yeah, what are
I don't
these
think
things?
That they're real. I think it's probably the dominant view among philosophers of math that they're not real. I mean, that there are
triangles certainly very are not
real. Well, in a Platonic sense, I mean, so most, and then I would think that most philosophers of mathematics who do believe in mathematical objects sort of construe them as sets, and that sets have a Platonic existence. But the other example I was going to say, Leibniz, he didn't believe in the existence of actual infinities or these actual infinitesimals, but they were a tremendous tool for solving mathematical and physical problems. And it's similar, I guess.
That's a great analogy. That's a great analogy. Yeah.
Good. I'm glad. But you can't directly test the existence of a string, or you don't think that will be the case, but they're incredibly useful for solving these outstanding problems.
I think it was my colleague Subir Sachdev who actually took my course when I was teaching string theory, and then later went on and used ideas from string theory to solve some problems in condensed matter physics.
That's great.
Yeah, so he solved some problems in condensed matter physics, and you could have solved them using known techniques. With hindsight, you could have used other methods, but you never would have put it together that way, sort of insights from string theory. And I think it was him that said string theory is the calculus of modern theoretical physics. It's a tool. It's a set of mathematical relations that is an indispensable tool for many enterprises in theoretical physics. Making your analogy to Leibniz more precise, yeah.